I want to talk about how we can use entropy to reason about whether reactions are going to be spontaneous or not. Really, by spontaneous, we mean, is the reaction going to happen in the forward direction as we wrote it in a chemical equation? Is it going to proceed, and therefore, can we use that reaction to do anything productive? So entropy, we've discussed, is this quantity S, our measure of randomness or mixed upness or disorder or spread outness in a system. Delta S measures the change in that. Is the system becoming more disordered or less disordered? The key to connecting spontaneity and entropy is the second law of thermodynamics. There are many ways to state this in various mathematical forms. The way that casually and conceptually works for us is that if a reaction is spontaneous, it increases the entropy of the universe. You may hear that backwards. The entropy of the universe increases for all spontaneous processes. Really, what it's saying is one of these doesn't happen without the other. Spontaneous processes always increase entropy. The key to discerning whether this is going to happen, because the universe is a big place to think about, is our secret that we can break the universe into two chunks. The system, which is what we're talking about in our chemical equation, and the surroundings, which is everything else. If we can reason about those two things separately, we can put them together and state facts about the entire universe. How are we going to get to those? We'll fit them in two slightly different ways. Remember that these two can either both be positive, both be negative, or they can be mirrors of each other. They're not directly connected to each other. The delta S for the system, the best way for us to determine that is going to be to look at the reaction equation and use those hallmarks of entropy increasing that I talked about in my previous video. For the surroundings, what we're going to want to look at is the energy flow associated with our chemical process. Because the surroundings aren't chemically changing in our reaction, the only way we can influence their entropy, their disorder, is by putting energy into them and therefore heating them up, which we know makes things more disordered, or by taking energy out of them, cooling them down, making them more ordered. That's going to be our key to thinking about the surroundings, whereas the chemicals listed in the equation is going to be our key to thinking about entropy changes in the system. How do we connect these two? So, if we have a process where the system is losing energy, a process that we normally think of and describe as exothermic, releasing heat. So this is something where if I held it in my hands, it would be warming up my hands. And that's a key statement there. My hands are not part of the chemical equation. They're part of the rest of the universe. My hands are gaining in energy, so the system must be losing energy that it dumps into my hands. So the energy change, the enthalpy change for the system is negative. The enthalpy change for the surroundings, through the first law of thermodynamics, energy is always conserved, is positive. The energy is gained by the surroundings, my hands. What that means is that the surroundings are becoming more disordered by virtue of being heated up. These three statements are inextricably linked to each other. Any one of them implies and requires the other two. So no matter which one you know about the other two here. Conversely, if we have a process that is endothermic, that takes in energy when it happens, the system would be gaining in energy, rising in H, so a positive delta H. The surroundings would be losing energy. Delta H for the surroundings would be negative, and therefore those cooling surroundings would be becoming more ordered. The entropy of the surroundings would be decreasing. Notice that the one thing I haven't connected to this is the delta S for the system itself. That is what we're going to need to look at the chemical equation for. So if we want to look at the delta S for the entire universe, We look at the chemicals in the equation to determine the delta S of the system. We look at the energy flow to determine the delta S of the surroundings. And if they both happen to have the same sign, this is really easy. If they're both positive, we know that the entropy of the universe is increasing and we're dealing with a spontaneous process. If both of them are negative, then the entropy of the universe is decreasing, and we're going to be describing a process that's not spontaneous. It wouldn't happen as written. What happens if they don't have the same sign? To think about that, it's going to be better to use a property called Gibbs free energy, delta G for the system, which I talk about in the next video.